Okay, last segment for this week, balancing chemical reactions. So here's a simple chemical reaction. It's the synthesis of water by combining hydrogen with oxygen. And so hydrogen always has to be diatomic H2, oxygen also always diatomic O2. So remember, there were 7 elements that were always diatomic, and we talked about them a couple chapters ago, and they form a 7 on the periodic table. So go back and make sure you can remember which ones they are. So this is going to form water, H2O. We all know water's H2O. So then what does the balancing actually mean? It means that I have to have the same number of atoms of one element on one side as I have on the other, the same number of atoms of the other element as I have on the other. So I always just say, let's start left to right. So I do my checks and balances. I have 2 hydrogens on the reactant side, and I have 2 hydrogens on the product side. All seems pretty good so far. Now I have 2 oxygens on the reactant side, and I only have 1 on the product side. So the only way I can up that number is by using what's called a coefficient. The number out front is called a coefficient. The number below is called the subscript. You can change coefficients. You cannot change subscripts ever. Okay, so when I put that 2 there, I take care of my oxygens, but now I've changed my hydrogens. So then how can I fix it, or how can I readjust? I can put a 2 out in front. And so now I have a balanced chemical equation. And so I do my final count. I say 2 times 2 gives me 4 hydrogens. The 2 subscript here tells me I have 2 oxygens. And the 2 here tells me that if I distribute it there, I have 2 hydrogens. Sorry, I have 4 hydrogens. And then I distribute the 2 to the oxygens, and I have 2 oxygens. So everything balances out. That's a balanced chemical reaction. So here's another one. We've seen this one before. This is one of the sample problems from the lab. So I start left to right. I have 1 iron, 1 mole of iron. That's what that coefficient means. It's the number of moles in the reaction. And so if I go over here, I have 2 moles of iron atoms. So I have to get an equal number over here. I put a 2. Then I go and I look at my oxygen. I have 3 oxygen moles of atoms. So I'm going to have to put a 2 here in order to get 6. And then what I can do is I can put a 3 out in front here. But now when I do that, so the problem with the oxygens is that this 2 subscript means that I'm always going to have an even number of oxygen atoms. And this 3 here, I'm going to have to take care of that. So if I multiply this, I know at least by an even number, I'll always have an even number here. So then it just means making those even by multiplying by 2 to get 6. Then I have to adjust here. But by putting that 2 in, I've changed what needs to go here. So I have to change that now to a 4. And then let's just keep going. We'll practice a couple more here. So I look at the potassium. I have 1 potassium. I have 1 potassium. I have 1 chloride. But now I have that issue where I have an odd number of oxygens here. It's always going to be even on this side. So that would mean that I'm going to have to put a 2 out in front here to make those oxygens even. That gives me 6 oxygens on the reactant side. I'll put a 3 here, and then when I do that, I'm going to have to put a 2 in front of the potassium chloride. And so then we'll keep going to something a little bit more complex. I have iron here, 1 iron, 2 over here. I always just start left to right and see what happens. I now have 6 bromides, so I'll put a 6 over here. And when I do that, I have now 6 hydrogens, and I only have 2 hydrogens here, so I'll put a 3 in front of that. Now, when I do that, that 3 gets distributed to this whole sulfate polyatomic ion. So that means I now have 3 sulfates. And so what happened, that 3 I'm trying to show goes, so it's there. And so now by putting that 3 out in front there to help me take care of the hydrogens, I've now taken care of the 3 sulfates here. So the reason I want to do one of these examples is that typically if you just balance your polyatomic ion as a whole single unit, rather than separating it out to sulfurs and oxygens, it makes it a lot easier. And now here's a combustion reaction. And so if I look at this one, I have 7 carbons. So I'll start out right away. I always just go left to right, 7 carbons. Now I have 16 hydrogens. 16 hydrogens. I'm going to have to put an 8 over here. That gives me 16 hydrogens on the product side. Now I have 8 oxygens and 14 here. So that gives me a total of 22 oxygens that I have to deal with. Well, it makes it nice and easy because O2 is, I'll just multiply 11 by 2, and that would give me my 22 oxygens. So that's a nice, little bit more complicated. Here's another type of reaction. And if I could balance this one out for you as easily as possible, I have aluminum, I have hydrogen, 1 here, I have 2 here, I'll put a 2 out in front. But when I do that, now I have 2 chlorides and 3 chlorides. I'm probably going to have to put this up to 2 to make that 6. I always just try to make the odd numbers even. It tends to make things a little easier. So then that gives me 6 chlorides. So I'll cross out the 2. And now I have 6 hydrogens. So I'll put a 3 here. And I forgot about my aluminums. So now I'll go back and check my aluminum. So now I see I have 2 aluminums, 6 hydrogens, 6 chlorides. On the reactant side, 2 aluminums, 6 chlorides, because remember that 2 gets distributed, and then I have my 6 hydrogens. And then one last one here. This one's pretty straightforward, I think. I put a 2 out front here. That gives me 2 silvers and 2 iodides. I'll put a 2 over here. And when I do that, it takes care of this 2. And now I think everything's balanced. So I'm going to go back to each of these reactions and talk about them as a type of reaction. So there's 4 types of reactions that we need to know for this chapter. And they are, 5. The synthesis reaction, which is where you have 2 species coming together to form one. So I always say you can recognize a synthesis reaction, maybe a general form of it is A plus B yields C. A plus B yields AB, something of that nature. And then a decomposition, this one, the potassium chlorate, is a decomposition reaction. And this is a scenario where you have a single component breaking down into 2. So you have an AB breaking down into A plus B. And then this one's considered a double replacement reaction. And the double replacement reaction can be thought of like this: A, B, plus CD goes to AD plus CB. What happens in the double replacement reaction is that I always say they change partners. A is with B here. Now A is with D on the product side, and C is with D here, but C switches with B. So it's really all about the positive and negative ions switching partners. And we'll talk more about this type of reaction next chapter 4. And then the combustion reaction is always a hydrocarbon reacting with oxygen, and the hydrocarbon reacting with oxygen always produces carbon dioxide and water. And that's just a fact you need to know. And then there's a single replacement reaction. In a single replacement reaction, something like this happens. The aluminum kicks out the hydrogen to form aluminum chloride and releases the hydrogen. So one species breaks up a species that's made up of two components and replaces one of the components and releases the other. And then this is just another example of double replacement, a little bit easier. I have a positive Ag, positive 1, negative iodide, positive sodium, negative sulfide. Sorry, that sodium's a +1. Negative sulfide, -2. And here a +1 and a -2. Here a +1 and a -1. So this one's a little bit easier to see how the plus and minus switch partners. So the positive silver here is going to pair up with the negative sulfide on the product side, and the positive sodium is going to pair up with the negative iodide on the product side. So it's switch partners. That's all it is. So that's it. That's the end for this week.